Hey everyone, in this AP Chem series video, we're going to take a look at Maxwell-Boltzmann distributions. First, remember that gases are substances with particles that have very weak attractions between them. They're moving constantly, rapidly, and randomly, and you can calculate the kinetic energy of those gas particles with the equation 1/2 mv squared. In this video, we're going to take a closer look at how fast those particles are traveling and whether or not they all have the same speeds. Of course, we can do that with a Maxwell-Boltzmann distribution. It's simply a graph that shows the number of molecules in a gas sample traveling at a different speed or sometimes with a different energy. Here's one way to read a Maxwell-Boltzmann distribution graph. Take a look at the red line representing a sample of gas at 0 degrees Celsius. If we start by taking a look at the peak of that curve, we can see that this corresponds to the greatest number of molecules on the vertical axis. If I follow that same point downward, I would find on the horizontal axis the speed at which most of the molecules in the sample are traveling. You might have also noticed that there's actually 3 different lines on this one graph. Each of the lines here is representing the same sample of gas at different temperatures. The area under each curve is going to be exactly the same because that area represents the total amount of particles in the sample, and this is the same sample of gas just at 3 different temperatures. Here are some important things to notice about a Boltzmann distribution curve. First of all, a range of speeds exists. All the particles do not travel at the same speed. Even the very hot sample at 2000 degrees has some particles that go very slow, some particles that go very fast, and again, the peak of that curve represents the speed that most of the particles are traveling at. As the temperature of the gas increases, the average speed increases even though there will be some particles still moving slowly. At higher temperatures, there's just more particles that are moving faster. Lastly, even at high temperatures, there will always be some particles moving slowly. This is helpful in case you ever have to draw a distribution curve yourself. The line always has to start at the bottom left-hand corner. These 3 things make up some of the important key ideas related to these distribution graphs. Make sure you take some time and write them down. Let's close the video by looking at a different type of Maxwell-Boltzmann distribution. The one we just saw was the same gas sample at 3 different temperatures, but other distribution curves will show different gases at the same temperature. And they're showing very different things, even though they look pretty similar. You might think that different gas particles, as long as they're at the same temperature, should have particles traveling roughly the same speed, but this graph points out that that's just not the case. The xenon line in purple shows that the xenon particles are traveling at much slower speeds on average compared to the helium particles that are traveling much faster. To understand why that is, the first thing we have to do is bring back one of the components of the kinetic molecular theory, which says that any gas at the same temperature will have the same average kinetic energy. Since all of the gases on this graph are at the same temperature, I could choose any 2 of them and write a little mathematical representation of this statement. For example, the kinetic energy of the helium particles must equal the kinetic energy of the xenon particles. Next, we can substitute in our 1/2 mv squared from the kinetic energy equation onto each side of this mathematical expression. So on the left-hand side, I'll have 1/2 mv squared for my helium atoms, and on the right side, 1/2 mv squared for my xenon atoms. Now let's look at how the 2 sides of this equation are going to be different, first in terms of mass. From the periodic table, I can see that helium particles are much lighter and xenon particles are much heavier. So there's going to be a very low mass or a small number over here and a very high mass or a big number over here. Now let's think about how the velocities are going to compare. The only way that my helium side of the equation with a very small number plugged in for mass, the only way that that's going to equal the kinetic energy of the xenon particles with a much greater mass is if the velocity sort of makes up the difference. In other words, the velocity on the helium side must be much greater so that it equals out the xenon side. That's why on the distribution curve, the helium particles have a much greater average speed. At the same time, my xenon particles with a much greater mass, the only way they are going to equal the kinetic energy of the lighter heliums is if the velocity is much lower. That's why on the distribution, my xenon particles, most of them, are traveling at a much slower speed. We can summarize this by saying that if at the same temperature, lighter particles will move faster while heavier particles move slower. This is another one of the key ideas for the video. Make sure to take some time and write it down. And that also concludes this video on Maxwell-Boltzmann distributions. Thanks for watching, and here's a brief summary.